We now consider various technologies that take advantage of the properties of the nucleus and radioactive decay and nuclear reactions. We begin with talking about artificial nuclear reactions, which would refer to nuclear reactions that we cause, we take advantage of, we initiate, as opposed to all of those that occur naturally in the Earth's crust and in the upper atmosphere as cosmic rays come into our space. There are many naturally occurring isotopes, and there are many isotopes that do not occur naturally that we have created by means of artificial nuclear reactions. In fact, we're now up to several thousand different kinds of nuclear reactions, and we have synthesized thousands of different types of radioactive isotopes. This process is often called transmutation, to mutate or across. In other words, to change from one type of nucleus to another type of nucleus. Excuse me. The word mutation comes from the Latin word mutato, and if you want to know the other forms of it, mutatavi and mutatus, meaning to change, and having changed. Remember that from 10th grade. In any case, we are actually creating a new isotope from a different isotope. The example here in your text is if we take an alpha particle and we accelerate it and manage to smash it into a nitrogen atom, its nucleus, the nitrogen atom will transmutate into an oxygen-17 nucleus and shoot out a proton. Now, of course, if you're going to fire one nucleus at another nucleus, you're going to have to overcome the repulsive forces that they each have because they're both positive. And that means you really are going to have to accelerate that particle. And you usually accelerate the smaller particle and aim it at the more massive particle. These particle accelerators are located in various places around the country and around the world. Talk a little bit more about that later. And they basically take advantage of the fact that because the particle you're accelerating is charged, if you make the region of space, the region of a tunnel or a tube, immediately in front of your particle having the opposite charge, your positive charge particle will be attracted and therefore accelerated into that negative region of space. And then as soon as it enters that negative region of space, you make it a positive region of space, and the next region in space in front of it, negative. So it's repelled by the space that it's in, attracted to the space in front of it. It accelerates even more, and you keep doing that, and some of these particles then end up traveling at near light speed. Now, in the picture at the bottom of the page, you see Glenn Seaborg, who I actually had a chance to meet back in the late 70s, a couple years before he died. He was about 6'8", very, very gracious and kind. I was with about 10 other science teachers from around the country and a few from out of the country. And he signed a periodic table for each of us because the discussion was that element 106 was going to be named after him. And indeed it eventually was, Seaborgium, and the debate at the time was whether to wait until after he died before they named the element after him. And of course, that wasn't a fun kind of consideration, and so they didn't wait to award it posthumously, but they awarded it to him shortly after I had a chance to shake his hand. He was a gentle giant, but he was instrumental in operating at the University of California, Berkeley, a particle accelerator, to discover a lot of these transuranium radioactive isotopes. He actually is one of, at least half a dozen or so Nobel Prize winners that I've had a chance to meet over the years. And this leads right into the next page of our book, talking about how do we make these new elements? What are some of the challenges involved? What do we hope to learn from this? Of course, the more we learn, the more we're able to accomplish, the more we're going to understand the structure of the nucleus. And as I've said before, the deeper we probe the nucleus and the more we discover by smashing particles into nuclei, we discover that the nucleus seems to have a structure kind of like electrons do. And just like electrons are in various shells, and there are rules that govern those electrons in those shells, think of the quantum numbers, and things happen when electrons jump from one shell to another or fall back. There seems to be an analogous kind of thing going on with protons and neutrons and their location and their activity inside the nucleus. And of course, that's an important lesson. We should always expect that the deeper we probe something, doesn't matter where in the universe it is, the more you probe something and learn about it, the more levels of design and genius and brilliance and intricacy and complexity you should expect to find. Because after all, creation reflects the Creator. Now, in this page, you can also see that two of the elements up here, technetium and promethium, do not occur naturally on the planet, and those are the only two clear boxes on the periodic table, if you remember the one in my room, less than element number 92, uranium, that do not occur naturally. A lot of this work was done at the Lawrence Livermore Laboratory in Berkeley, California, University of California, Berkeley. We have a particle accelerator there. There's one in Dubna, which is near Moscow. There's another one in Darmstadt in Germany. And Japan has recently added one as well, if I remember correctly. And you might recognize that some of the newer elements have been named after these locations. For example, element 105 is called dubnium, named after the particle accelerator near Moscow, and element 110 is named Darmstadtium, named after the particle accelerator in Germany. Over in the right-hand column, we used to name elements according to, initially at least, according to the Latin. For example, element 117 would be UUS, which would be uno septum, meaning 117 in Latin. And if you look at older periodic tables, you will see a lot of those three letters representing three words in Latin. In the last 2 years, we now have officially agreed upon the names for all the elements in that last row of the periodic table. And Flerov there, which is one of the laboratories in Dubna, and instrumental in discovering some of these isotopes, is now the name for element 114, flerovium. So you should know the vocabulary word transuranium, meaning beyond uranium. Every element beyond uranium does not occur naturally on the planet, but actually can be produced through nuclear kinds of reactions and bombardment. Some of them have longer half-lives than others, especially plutonium, which has a long enough half-life that we can use it in nuclear reactors as a fuel. You notice another individual's name, Enrico Fermi, just a genius and a gentleman, and both in nuclear physics, but in all kinds of things that are mechanical. The story is told that one time he was traveling across country, and here's one of the greatest nuclear physicists in the world. He stops at a gas station to get some gas, and a mechanic is working on a car and having trouble fixing it, and Enrico walks over and is able to fix it on the spot, and he was immediately offered a job to work at that gas station. He did turn down working at the gas station and continued his work in nuclear physics. But fixing cars requires a unique kind of skill and talent, one that is often not appreciated enough in our country, which is symptomatic of a lot of skills that many people have in the area of construction and carpentry and electrical and plumbing and so forth. The ability that individuals have in these areas should be appreciated just as much as abilities in medicine and in nuclear physics. How we make these transuranium elements is pictured in some of these equations down here towards the bottom of the page. For example, how can we make plutonium, which is a very valuable element in fuel, nuclear fuel for a nuclear reactor. And we take the uranium-238 that is not fissionable, that doesn't split when a neutron hits it, and if we configure our nuclear reactor correctly, which has 5% uranium-238 that does fission and 95% uranium-238 that does not, and we line our reactor vessel with that uranium-238, it can actually absorb neutrons and turns into uranium-239, the first of the three equations that you see. And then uranium-239 undergoes a natural beta decay twice till it becomes plutonium-239. Then we can harvest or extract the plutonium-239 to use it in our research or to use it as a fuel in nuclear reactors. It is also a way that we make americium-241. And americium-241 is used in our smoke detectors. Now, one practical application is nuclear fission. Fission means to split a large nucleus. It would be almost impossible with present technology to split smaller nuclei. But bigger nuclei, which are slightly naturally unstable, if you remember that curve where you have the strongest binding energy in the middle, in the vicinity of iron, towards the right, just not quite so much strong binding energy, are the very, very large nuclei. So you can split them, and they become a little more stable and release a lot of energy. These nuclear reactions here don't show that energy, but one of the things it does show is that some of these splitting of nuclear isotopes, especially uranium-235 and plutonium-239, when you hit them with a neutron, will create more neutrons, 2 or 3 additional neutrons, and those neutrons can do the very same thing that the initial neutron did in that first reaction. And so you need 1 neutron, and you get 3. Those 3 can strike 3 nuclei, producing 9, which can strike 9 more nuclei, which can produce then 27 neutrons, which can strike 27 nuclei, which then can produce 81 neutrons, and so forth. And very rapidly, you have what we call a chain reaction. Obviously, you can see from this process that the way to control a chain reaction is by controlling the neutrons. Now, here's a very important point. In a nuclear reactor, you only have 5% uranium-235. It is impossible for a nuclear reactor to blow up like a nuclear bomb, which has to have over 90% uranium-235. In a nuclear reactor, since you only have 5% uranium-235, it is relatively easy to control the number of neutrons that will go on and split other nuclei. You actually have control rods which absorb neutrons, which you can drop down into your reactor vessel whenever you need to slow down the chain reaction or to stop the chain reaction altogether. And indeed, one of the passive safety features in American nuclear reactors is that should anything happen in the nuclear reactor, a loss of electricity, that might turn off or disable the ability of pumps to pump away the hot water that is capturing the heat. These control rods are under the influence of gravity and will naturally, because they're being held in place by electromagnets, if the electricity goes out, they naturally fall down into the reactor vessel, absorb the neutrons, shuts down the nuclear reactor. Now, I say this because yesterday, as I am doing the screencast at this moment, was the tragic anniversary back in 1986 of Chernobyl. And the design of Russian nuclear reactors is terribly unsafe and cobbled together and totally disregards the safety of individuals. But of course, remember what communism, atheism is all about. It's the success of the state and not the flourishing of the individual, according to that worldview. And so they did not have this kind of passive feature. And so when it overheated, it produced so much radioactive steam that it just blew everything apart. Not a nuclear blast, but a steam blast, and radiation then spilled out and began to travel downwind. And another safety feature of American reactors that Chernobyl did not have is a containment building over the reactor vessel itself. Now, a nuclear bomb with over 90% uranium-235, what stops a nuclear bomb? Well, the actual explosion stops itself, because once you've blown the uranium-235 way far away, the likelihood of neutrons striking those 235 nuclei is practically zero, because they've been blown so far away. And so a nuclear bomb, I should say a nuclear fission bomb, shuts itself off as soon as it's detonated. You hate it when a nuclear bomb keeps blowing up and blowing up. So a nuclear fission requires 3 steps. You have to initiate the nuclear reaction, the chain reaction, by having a neutron source that can shoot that first neutron at the 235 nuclei. You need to have a configuration so that the likelihood of the 2 or 3 neutrons being produced is high for striking other 235 nuclei. That's the propagation step. And the design of your nuclear reactor depends upon that. You have to have what we call a critical mass, enough uranium-235 in one place and in a right geometry, so that the likelihood of 235 nuclei being split is high. And then you have to have a way of terminating or shutting it down. And that you do that by controlling the neutrons with reflectors and with absorbers, such as control rods. And by controlling these neutrons, you can control the nuclear reaction in a nuclear reactor. Control rods are often made out of cadmium because they absorb neutrons really well. The 2 kinds of fuel, as I've talked about even way back in honors chemistry, uranium-235 and plutonium-239 are the only nuclei worth mentioning that will split. And we've mentioned before that uranium-238, the common isotope of uranium, 99.3%, uranium-235, about 0.7%. And so when you mine uranium out of the Earth's crust, you need to refine it. You need to enhance the percentage of uranium-235 from its natural 0.7% up to about 5%. And we do that in a number of different ways, using centrifuges. They mention that right here. We can also use technologies having to do with membranes and gaseous diffusion. In either case, we take advantage of the fact that the 238 nucleus is slightly more massive than the 235 nucleus. And right now, for example, in Iran, just in the last year, they've announced they're up to 20% with their centrifuges in enhancing uranium-235, which makes you wonder, and there's really no question what's going on here, why they need 20% when they have all of this oil and a nuclear reactor only needs 5%. So you can see how geopolitical this kind of discussion is. And it would not surprise me, and this has already happened a few years ago, when a computer bug disabled the computers that were regulating all of their centrifuges and set Iran back a number of years, that their centrifuges, which are deep underground, at some point might experience a bunker-busting bomb drop. And Israel, who certainly has their very existence depending upon what's going to happen here, with the assistance from the United States, might have something to say about this. Right now, in the United States, we have about 100 operating nuclear power plants. Some of them are 40 to 50 years old. Around the world, we have about 400. In the United States, just slightly less than 20% of our electrical energy comes from nuclear, and about 17% of the world's energy does. Some countries, it's much higher percentage-wise than the United States. There have been some disasters, and like I mentioned, Chernobyl back in 1986. There's a book I plan to read this summer about Chernobyl. I think it's called Midnight at Chernobyl, and really shows you the consequences of this worldview, and even in the production of technology and energy, and how you respond when there is a disaster. Maybe 40 people or so died. The initial nuclear reactor operators who were undertrained and performing an experiment, and that revealed the inferior design of Soviet reactors. Then there was the one in 1986. Back to Chernobyl, I should mention that the other 30 or so deaths were the first responders, and there will be some deaths and have been some deaths due to cancers over the years. Back in 1986, there was 3 Mile Island. One of the reactors there experienced a meltdown, and again, this was a malfunction of a valve, and the operators actually overreacted, pardon the pun there. All they would have had to do was back away and let the system shut itself down, but in their response to a valve that was not functioning correctly, and a gauge then that gave them misleading information, they actually inadvertently shut off the coolant water, and it melted down. Interestingly enough, the number of people who were killed or injured in this, the number was actually zero, the number who were killed, and the incidence of cancer or maybe birth defects or miscarriages went down because all the people that lived in the area, and this is in central Pennsylvania near Harrisburg, actually went down because they went to the doctor more, just to be on the safe side. We might say that one of the problems right now with social distancing and all the hospitals being shut down and only operating in the case of treating the virus is an awful lot of people aren't seeing the doctor and aren't being treated for various things that they ought to be treated for. And I should also mention that this waste material from 3 Mile Island eventually gets shipped out to Idaho for study, in the very place where I spent all my summers of research. We could also say that replacing the energy lost by the nuclear reactor that was destroyed at 3 Mile Island, if you replace that with a coal power plant, every time you burn coal, huge amounts of radioactive material and dust and debris and soot and, of course, carbon dioxide does get emitted into the atmosphere. Here is a graph showing you the percentages of electrical energy generation. A couple of years ago, you might remember that Japan experienced the consequences of a huge earthquake that produced a tidal wave that took out a number of their nuclear reactors on the coast at Fukushima Daiichi. And as a result, they are not using as much nuclear energy as they used to. So this number down here of about 25% has gone down for Japan. Nuclear fusion is a goal that maybe someday we'll be able to harness the energy that stars use in order to generate electrical energy. And fusion requires you to take small nuclei, such as H2, which would be deuterium, 1 proton, 1 neutron, and maybe tritium, H3, and fuse it together to produce energy. There's not much radioactivity going on with this at all, and you get maybe 7 or 8 times the energy per nucleon in fusion. The problem is, how do you get the high temperatures that it takes to fuse nuclei together? We'll use these gigantic lasers, and we actually generate temperatures that are hotter than the interior of the sun, more like the surface of the sun. And the material that you make and what a star is made out of is called plasma. It's that fourth state of matter, perhaps the most common state of matter that we know of in the universe, because it's what stars are made out of. And of course, this is before we get much understanding in terms of what is dark matter and dark energy. So you might say, well, what kind of container can you put this plasma in as you try to carry the heat away to turn water into steam, and the steam then can turn your turbines to generate your electrical energy? And the answer is, well, it's not Tupperware. You actually have to suspend it in an electromagnetic field so that the plasma doesn't touch anything. And I think for years now I've heard in the news reports that we're at the break-even point, where the amount of energy it takes to contain your plasma and the amount of energy it takes to fire up your lasers is equal to the amount of energy that you're getting out. So we're probably still just over the break-even point here. Now, as far as safety is concerned, we need to think about how are you going to measure radiation? And there are lots of different units of radiation. I've told the story before when I took my nuclear reactor physics course in graduate school back in my master's training. There were 5 of us in the class. 2 operated nuclear reactors. 2 of them were completing their PhD in nuclear physics. And then there was me, the physics teacher. And because I could do dimensional analysis problems and convert from one unit of radiation to another, I'd get the math problems right. And these other guys had trouble with that. And it was a little unnerving to think that guys operating nuclear reactors had a little trouble with this basic algebra. In any case, we have the unit called the Curie and the Becquerel, which are various disintegrations or decays per second, and named after Marie Curie and Henri Becquerel. We have some other units as well, the Gray and the Sievert. We have named after other physicists. We also have the kinds of units that are acronyms. For example, the RAD, a radiation absorbed dose. And we have the REM, which is often what you see in the literature, or at least in discussions with the public about quantities of radiation. The REM stands for the Rentgen equivalent man, or radiation equivalent per man. And the REM is a rather large unit, so typically we talk about millirems. And we'll mention more about this in just a few seconds. But one thing that's important to remember is it's not just how much radiation you or a worker in the field might experience. It's what part of the body has been exposed, and it's also whether this exposure is chronic over a long period of time or a single large dosage. It also depends whether it's an alpha, beta, or gamma emitter. And all of these factors must be taken into consideration when we talk about this, the effect that radiation has on, for example, the human body. They mention down here the quality factor, which is a number usually less than 10. Oftentimes it's a 5. For example, for low energy protons and neutrons, it's a 20 for alpha particles, because remember, they are big and bulky and they can have a huge effect as ionizing radiation should it get inside of your body through ingestion, inhalation, or injection. But it doesn't penetrate very well if it just strikes the surface of your skin, which can block it. So everything around you is radioactive naturally. We have this, what we call background radiation. AP Physics, even today, is doing a lab on radiation and the half-life of a particular isotope. And when we talk about background radiation, we have radioactive particles coming in from outer space, radioactive particles producing other radioactive particles through collisions in our upper atmosphere. We have radiation that is naturally occurring through decay of uranium and other things in the Earth's crust. We have the kind of radiation that we produce. We have residual radiation from when we used to test our nuclear bombs back in the 60s above ground. Nuclear tests now are required to be done below ground. And there haven't been many of them, but every now and then we pick one up from, say, Russia or China. And so we have all of these different kinds of exposure to radiation. Now, the last paragraph on the page says the average radiation dose that you or I might have during the course of a year, normal exposure is about 200 millirems per year from background. And then you get some more radiation, for example, if you have various medical procedures. And some of it is the kind of radiation you want to have, because not having these medical procedures is worse than the radiation that is used when you have these medical procedures. Think, for example, of X-rays when you go to the dentist. And so if you were to try to calculate how much radiation you're exposed to, you can see some average levels here per year. And where you live would be a big factor. The higher in the altitude that you live. If you live in Denver, you're going to get more than in St. Louis, because you're at an altitude of about almost 5,000 feet higher up. And so there's less atmospheric absorption of radioactive particles from outer space. If you fly in an airplane a lot, you're going to get a lot more. If you have to have a lot of medical procedures, you're going to get more. If you actually work in the nuclear field in nuclear medicine, or in mining nuclear material, or in the nuclear weapons field, or nuclear cleanup, you're going to get more. And as we study this radiation, we don't have a large data set of individuals to study the exposure. We often have to use animal proxies, which aren't as good. But we do have, for example, we study the people that have still surviving from Hiroshima and Nagasaki. There have been various contaminations from nuclear spills, nuclear mining, sometimes the improper disposal of nuclear material from medical equipment. For example, back in, I think it was, it might have been 87 or back in the late 90s, a medical device was thrown away in a dump down in Brazil, and people started playing with the source of cesium, and there was a number of people that died from that in a family, tragically. But we study these kinds of exposures, and that's how we begin to learn a little bit about the problems that people might have as a result of exposure. So, the way that I often talk about this is I round up the average yearly dose that a person might get. At the high end, you might get maybe half a rem, about 500 millirems, maybe twice the average background dose. If you multiply that by a factor of 10, you get the government limit in terms of how many millirems per year you're allowed to be exposed to if you work in the nuclear field. If you multiply that by 10, then you get this number of 50 down here, which is where we begin to see an actual biological consequence, a decreased white blood cell count. And of course, the white blood cells, the leukocytes, are involved in your immune system. And you can recover from an exposure to this many rems of radiation. And the government typically looks at the level of detectability when we see biological effects. You divide by 10, and that becomes the limit, factor of 10 safety factor. And then you go 10 times that, and now you're up to here, and now you have what is often called LD50, the point where you get a lethal dose at which 50% of your population, if exposed to that, would die. We have different ways of detecting radiation exposure. The times when I have worked with radioactive material back out in Idaho or out in a cancer research where we used some radioactive material, I would have film badges like this that periodically a health physicist would look at to make sure that you're staying under the limit of exposure. And we're going to stop right there, and we will then talk about applications of nuclear chemistry later.